Hello and welcome to this course on model predictive control. In this week we are going to move on to state space MPC. Okay. So, the state space model that we are going to talk about is xk plus 1 equal to axk plus buk and yk equal to cxk. Okay. But as we have studied so far, this particular model structure is not sufficient. We need to add a few more things to the model. Okay, so let's recap what we had done in the DMC part of the course. In the DMC part of the course, what we had said, this was week 3, week 4, week 5 of this course. What we said is that there are other things that are also present in the overall scheme of things. In addition to the manipulated inputs, we also have measured disturbances. Measured disturbances are inputs that we cannot manipulate. We can measure the effect of those inputs is modeled. However, we cannot manipulate those inputs, and those we represented in the form of some structure SD multiplied by delta dk. Okay. In addition to that, there were unmeasured disturbances and errors in the model and plant, which we called as model plant mismatch. And to handle model plant mismatch and those errors, we introduced the term EK. EK was nothing but the error or the bias between YK and Y measured. Okay. And based on that, in the DMC algorithm, what we did was we set up YP k plus 1 as nothing but m multiplied by y tilde k plus SU multiplied by delta UMK plus SD multiplied by delta DK plus IP multiplied by EK. This was how we set up the prediction equation. Okay. Maybe I should change the color. This probably blue color would be more appropriate. This perhaps I can use purple. Okay. So, this was how we had set it up in DMC. Okay. What we did in the last few weeks, okay, we said that LQG is LQR plus Kalman filter, and when it came to the LQR part, we actually had the equation same as before, xk plus 1 equal to axk plus buk and yk equal to cxk, and then we did some amount of augmentation. In LQR, augmentation to handle set point tracking / disturbance rejection cases. Okay, and then in Kalman filter, we basically talked about disturbance modeling. To ensure that errors were IID or Gaussian white noise. Okay. So, what we are going to do in this module is to combine these two concepts for state space MPC. Okay. So, I am going to try to bring in some relationship with what we have done in the DMC, what we have done in LQ control, and use those for state space MPC. Okay, we are going to do this in two parts. First, I am going to talk about the deterministic case, the deterministic state space MPC, and then we are going to talk about the stochastic case. And the model that we talked about earlier in the DMC algorithm was of the form, say we have G, then we have our GD, and we will just call this as W. Okay, and this was the overall structure that we had. One of the assignment problems that you guys did, and this is for the 2020 batch, the assignment problem that you looked at. So, the example of the error between model and plant, and this was one of the assignment problems that you did. This is for the 2020 batch, that the G plant was given to you as 2.75 e to the power minus 6.2 s divided by 18.5 s plus 1, whereas G model that was assumed for MPC, if I remember correctly, it was something of the form e to the power minus 7s divided by 20s plus 1. So, if you took the step response of the first guy and compared it with the step response of the second guy, you will see that the two step responses are different, the two model predictions are going to be different, and therefore, we had this error term IP multiplied by EK, this particular term that we added in order to do the bias correction. Okay, so we need to do something equivalent of that in order to ensure that the state space MPC also has the integral action in it and also is able to get rid of disturbances of this nature. Okay, so in the forthcoming videos, what I am going to first do is talk about deterministic state space MPC, and then move on to the stochastic state space MPC, where we will combine the MPC concepts with the Kalman filter concepts in order to do stochastic feedback control. Okay, so thanks and see you in the next video.